Okay, the next speaker is Tilen Cadez from IBS TCS. Right? So he's going to talk about metal-insulator transition in infinitesimally weakly disordered flatbands. So let's welcome our speaker.
Can you hear me? Is
yes,
the sound?
Yes.
Okay, so first I would like to thank the organizers for inviting me to present my work. And I think we just had a really nice talk by Professor Römer on the topic that will kind of maybe seem to just nicely blend with what I want to say. Which is our recent work on metal-insulator transition in infinitesimally weakly disordered flatbands. So the aim was to try to make a systematic study of a much simplified all bands flat system. So flatband systems we know are highly fine-tuned systems, which is a subset of, let's say, some lattice systems, for example. But all bands flat are the subset of subset. And we want to see what is the, what does infinitesimal weak disorder do in this case, and whether we can find some interesting transitions. And this work was done together with PhD student Yong-Jun Kim, which recently joined PCS IBS, and he did excellent work on this that I will show. And he's working under supervision of Alexei and Sergey, so, which were also involved in this work. So the outline of the talk is, first I will show an all-band flat construction, which will kind of give the idea that there's a whole manifold of all bands flat systems. So despite them being fine-tuned and rare, there is still certain freedom in finding these systems. And then we will apply infinitesimally weak disorder in this type of systems. And I will show how one can get a scale-free model. And I will give examples in which show that in 1 and 2 dimensions, we get localization, and in 3 dimensions, we find a metal-insulator transition. Just to go through the basics really fast. So I will consider periodic lattice systems, non-interacting. So we have a unit cell with new lattice sites in a unit cell, and due to translational invariance, we know we can get a band structure. So momentum is a good quantum number, and the bands will in general have certain dispersion, but as the topics of this conference are basically about flat bands. So in certain cases, we see dispersionless band. And in this talk, I will consider all bands flat case. So let's go to construction. So consider a set of sites. So this is example now of two-band systems in two-band system in 1 dimension. So we have disconnected sites, and I will give the lower sites energy EA and the upper sites energy EB. This if we have a set of such ranks, we will have a unit cell, and of course we will have 2 flat bands at the 2 energies. But now what we can do is we can apply local unitary transformation on each of the these rungs in a ladder, so up down, and this is a general local unitary transformation. It's an SU2 matrix which is parametrized here by 3 angles, and this leads us to the picture in panel B, which shows connected sites, connected dimers. And now we perform a second local unitary transformation, but now in this redefined unit cell. So this transformation will lead us to fully entangled picture, and we will have this kind of structure. And so far, I haven't done anything. This is still the same two-band, all-band flat system. So basically, for any choice of these parameters, this is a manifold of equivalent all-band flat systems. So for example, Kreuzladder is a known case, which is depicted here, and it's been introduced in already some time ago, and it can be easily solved. So in periodic case, you get two dispersions, and now you can see that when the hoppings on the diagonals and on the rungs are of the same magnitude, you will get an all-band flat criterion. So there will be just two flat bands. And Carlo came to save the day again, and he found local unitary transformations in this preprint that map basically our disconnected picture to the fully entangled picture. So basically, for choices of theta angles pi/4, we see that this gives us Kreuzladder and connects the disconnected sides. So note also here that when I choose theta to 0, this will remain disconnected. So this will kind of be a trivial case. So no hoppings. Now we can continue the same sort of constructions. So we have these sort of ladders, and we connect them along the perpendicular direction with the third local unitary transformation and obtain this kind of structure. And this will be our two-dimensional two-band all-band flat systems. And we can, of course, do the same in along the third dimension and obtain the 3D system. Now, at this point, we want to apply add potential on-site disorder, and we add it on each of the sites and choose it to be a random box disorder. So like in Anderson model, like in normal Anderson model. And now what we do is we apply inverse local unitary transformations. So our total Hamiltonian would be the initial just diagonal part plus the transferred part, which where U dagger is the inverse transformation. So it's a set of two local unitaries in one-dimensional case, three local unitaries in two-dimensional, and four local unitaries in three-dimensional case. And D is diagonal matrix with random on-site disorders. So now what we are interested is infinitesimal disorder. So when disorder is much smaller than the gap between the two flat bands. So this would be a picture. So due to the disorder, the energy of the states will change, but it will change up to the order of W. And when this is much smaller than the gap, it shouldn't affect, so the states living at one flat band shouldn't feel the second band. So what we do is we just project, so basically cut out half of the system and obtain a scale-free model coming, because W is a prefactor in the scale-free Hamiltonian. So for in one dimension, what the model that we get this way is basically nearest neighbor hopping model with on-site energies Vn and hoppings Tn. And we can obtain it here. So it's a function of the manifold angles and a function of the on-site energies. So it's a sort of correlated disorder where we have correlation in both potential and hoppings. But you can see that basically the phi angles appear only in the phase of the hoppings. And this is a global phase, so it can be gauged away, so it doesn't affect localization properties. So basically, in 1D, there are only two parameters, and from the structure of matrix elements, you can see that it suffices to consider the two angles to be between 0 and pi over 4. So the pi over 4 would again correspond to disordered Kreutz, so the Kreutz ladder with potential on-site disorder, and the 0 angles would correspond to just decent angle sites where we just put disorders. So in this case, of course, except changing the energy, the states remain compact and localized at each of the sites. So what we do then is, in order to reduce the number of parameters, we just set the two angles to be the same. So being between 0 and pi over 4. And we perform numerics on this case. So specifically, we did exact diagonalization and transfer matrix, but I will just show the exact diagonalization results here. So I show in the first picture, so on x-axis is the angle theta, and here on y-axis is the average participation number. So participation number is given here. It's just the sum of the coefficients of the mute eigenstate to the power of 4, the inverse of that. So when participation number is 1, it means one site is occupied. If participation number is 10, 10 sites are occupied, and so on. So what one has to look at is how the average participation number scales with the system size. So here I show two system sizes, and you can see that the results overlap, meaning that this participation number remains small, and thus it shows localization. But already at this point, we see that our manifold of equivalent all-band flat systems is reacts differently to potential on-site disorder. So we see that at pi over 4, the states delocalize more compared to the theta 0, where states remain compactly localized. So all bands flat systems are not equivalent when it comes to disorder. Then we do similar analysis in the case of 2 dimensions. So it's this kind of structure. Again, we obtain scale-free model by removing the half of the sides, and we get square lattice and diagonal hoppings. And again, I will set the angles to be the same, just to reduce the number of parameters. So here now I show in panel B, so panel A is just the 1D case, panel B is the 2D case. I show now the average participation number again as the function of the angle theta. You can see that at large theta, we see some increase of the average participation number. So here L, now my system is of the size L square. So it is increasing, but the rate that at which it is increasing is the one that we should look at. So we look at how the average participation number scales with system size. And we determine the exponent alpha, and alpha going to 0 would indicate localization, whereas alpha going to dimension of the system, in this case 2, would indicate extended state. So you can see by increasing angles, here is a log-log plot, which shows us directly the slope. So the slope is directly alpha. We see there are finite size effects. So for largest theta equals pi over 4, there are still some finite size effects, but it indicates that the slope is tending towards 0. Furthermore, we also study ratio of adjacent gaps, which was previously very nicely introduced by Professor Römer. So I will not repeat the introduction of ratio of adjacent gaps, but I will just show our results. So we can see again that so the dashed blue line corresponds to the Poisson value of the average R, indicating uncorrelated energies, and this indicates localization. So we can see that by increasing system size, the average R goes towards Poisson value. So both these results tend to indicate that the states remain localized in 2 dimensions. Now, in a 3-dimensional case, we again do exact diagonalization. I will again set all the angles to be the same to reduce the number of parameters. And now I show the whole energy dependent plot. So in the left panel, you can see the extracted coefficient alpha, so how the participation number scales with the system size. And on the right side, I show the average ratio of adjacent gaps. And I promise I didn't talk to Professor Römer before. I think he used the same color scheme, blue, dark blue for Poisson distribution and red for Gaussian orthogonal ensemble. So basically, you can see from the results that we see a region of alpha tending to 0, and also ratio of average ratio of adjacent gaps tending to Poisson value, indicating localization or insulator. And on the other hand, we see a region where alpha tends to dimension of the system, and ratio of adjacent gaps goes to the value determined by the Gaussian orthogonal ensemble. So this indicates the metal-insulator transition. And moreover, you can see here there is a mobility edge. So the states at the band edge are localized, whereas the states at the band center are extended. And to zoom into the transition, we look at the energy 1, which corresponds to our flat band energy. And we look at the system size, different system sizes, the behavior of both exponent alpha and average ratio of adjacent gaps. So you can see that transition is clearly seen in both cases. And moreover, in the case of R, we can see here zoom into the transition region. We can see nice data. So we perform finite size scaling. So we can see that we get a nice data collapse, assuming that the average ratio of adjacent gaps is a certain function of x, where x is the critical angle in this case. So the difference of the angle to the critical angle times 2L to 1 over nu, where nu is the critical exponent. And from the least squares fit, we obtain the value of 1.54. And as we saw previously, this is in very good agreement to known results. And here I cite one of the results, but there are many where for the 3D Anderson model, which are around nu 1.6, let's say. So how can one understand this transition? So our theta equals 0 corresponds to no hopping, basically, and theta pi over 4 corresponds to maximal hopping. So basically, since the on-site disorder is already factored out, we have a case where disorder is kind of constant, but theta is changing our hopping. So basically, theta is our effective disorder strength. So that's why theta drives the transition in this case. So one can generalize this approach to new bands. So in this case, if we would have, again, all bands flat case, we would have SU new matrices, which have more free parameters. But we expect that basically as long as we consider infinitesimally weak disorder, meaning that disorder is much smaller than all the relevant gaps between the flat bands, one should in similar fashion obtain scale-free model. So one would expect similar behavior as reported here. Further generalizations are to consider other symmetry classes, so by either breaking time reversal symmetry and going to Gaussian unitary ensemble, or adding symmetry so that we have time reversal squaring to -1, so to go to symplectic ensemble. And another possible generalization is to consider other potentials. So to conclude, we have developed kind of a first step of systematic. It's still not general because we have which we limit to local unitary transformations. Of course, one could do unitary transformations which reach to larger distances. So this is kind of the simplest case. But which shows that even in infinitesimally weak disorder, one can obtain, basically, one can see that there is different effects of disorder for different all-band flat manifold representatives. So it leads in 1 and 2D to localization and to metal-insulator transition in 3D. As I mentioned, Young-Joon Kim was the guy that did all this, a lot of this nice work. So he will present tomorrow some additional results, specifically going beyond what is here and the ongoing work, which I kind of shown here, some of the generalizations. And with this, I conclude and thank you all for your attention.
Okay, thank you very much. Very much for the very interesting talk. Actually, we have plenty of time for questions. Yeah. So, any questions? Okay, Rudolf, please go ahead. Yeah.
Thank you, Tilen, for this lovely talk. Now I have basically I have two questions, but the first one is, so you start with something where everything is all bands flat, which would be compactly localized states. Then you put in this order and you observe a metal. So you must be basically breaking these all flat bands. Then they're no longer flat, right?
Yes, exactly. So except in the case when I choose theta to be equal to 0.
Yeah. Okay.
Then yes, then I'm breaking.
Okay, fine. I forgot my second question now, so someone can ask till I remember it.
Okay, so Victor, yeah, please.
Yeah, thank you very much for this nice talk. I want to understand better the word infinitesimal. So what does it mean that, as Rudo said just now, that you are breaking something with your W? And in this case, what is the comparison with this bandwidth EB minus EA? And should you observe some dependence on the system size? Because probably if you go to the infinite systems, any disorder will produce you this transition. Or on the contrary, for the infinite system, can you see this scaling of disorder together with EB minus EA and also with the system size?
Okay, so let me go maybe here, yes. So the total Hamiltonian is basically the part coming from the two flatbands and part coming from the disorder. And as you can see, the flatbands are basically these two, EA and EB. And our disorder, whatever it will do when it is small enough, it will just shift the energies here, broaden these energies in this range. So we will have no states in between or further out because the disorder can only kind of give energy, change energy of the order of W. And if this is much smaller than the gap, we expect to observe this kind of behavior.
You're saying that it is system size independent?
It is system size independent. It's basically what we get is a scale-free Hamiltonian. So W is just a prefactor. So I can just divide everything by W, whatever W is. So as long as it is much smaller than the gap.
Okay, and then, okay, proceeding with your answer. So the question is, let's say that you increase W by 2, by factor of 2. How it would affect this, your phase diagrams?
It would not.
Energy versus theta, which you shown in the end.
As long as this holds, as long as W is much smaller than the gap, we can do 10 W or 100, it will not change.
Okay, then the last question. When it will destroy your phase diagram? It should be half bandwidth or whatever.
This is, yes, this is the order when W becomes of the order of the gap. This is when we will have hybridization of the two bands. And this is where different effects will come into play.
So all the states will be delocalized in this case, or what? What is the expectation? On the contrary.
So in 1 dimension and 2 dimension, I would guess not. But in 3D, yes, it could be. It might be. So actually, this is what Professor Römer observed. I believe what he calls inverse Anderson transition. So I believe he was referring by works by Nishino, Goda, and Matsuda from, I think, 2006, 2007. This is where, as far as I know, the inverse Anderson transition was observed. But the thing is that in that case, you are coming basically from weak potential where you have no states, and you are basically passing the mobility edge. This is my interpretation of results. So we can see here that we have mobility edge, and there are no states available at lower or higher energies. And this is what was reported in the work by the Japanese group that I mentioned. And I believe Professor Römer is observing something similar. So if you are coming from the area where you have no states and you are going, basically you're going through the mobility edge, and this is kind of your inverse transition. This is my guess.
So disorder leading to delocalization. Okay, thank you very much. It's very interesting.
Thank you.
Okay, Rudolf, please.
Yeah, and remember my second question. Do you have a picture of the 3-dimensional structure of your models?
Not a nice one.
Can you show me a bad one? I mean, because I'm just struggling to see how that looks like. That would be.
So if one would be stacking this kind of layers, basically the 2D layers, and then you would have also kind of connections up and on diagonals, body and the plane diagonals.
And in which direction do you do transfer matrix with those?
Oh, I do only exact diagonalization. In 2 and 3 dimensions, we did only the exact diagonalization.
Yeah, okay. Thank you.
Mm-hmm. Thank you.
So, Victor, do you have another question, or you still have this? Yeah, you're still raising hand. Do you have another question?
Sorry, I didn't.
Oh, okay.
Didn't put it back. Okay, sorry.
Okay. Thank you. Any other question? Then let me ask a very, very simple questions. Actually, maybe you already explained it, but compared to the case with the flatband and one dispersive band, your two flatband system, how is it different actually? What's the role of the additional flatband for this localization property?
This is a good question. Yes, thank you. So actually, there was quite several previous works where people, so also Sergey and his group studied, which was also shown in previous work by Malte, the detangling where there were several cases. So in that cases, there was a flat band and dispersive bands. So as long as the flat band is gapped from the dispersive band, what they observe also is that localization properties kind of don't change when you go with disorder towards 0. So basically, independence of your localization properties on the disorder strength when you are tending to 0. This happens when we have gapped flat band. When the flat band and the dispersive band are touching, or when they are when the flat band goes through the dispersive band is different. So this can then lead to different divergences of localization lengths or critical states depending on dimensionality and also the CLS structure. So whether it occupies one unit cell or more than one. So this is kind of simplest case where CLS occupies one unit cell and bands are gapped.
So you mean basically the dispersion of the other band is not very important. Is it your conclusion? So especially your disorder is very, very weak, right? So I don't think that the dispersion of the other band is that important.
Yes, as long as the disorder is much smaller than the gap between the flat band and the dispersive band.
Yeah, thank you. So Nilanjan Loy, yeah, please go ahead.
Yeah. I have one small question. So for the clean case, how do you calculate the participation ratio? I mean, the question is whether the compact localized states form an orthonormal set for the example you have taken.
Yes, in my case, because I always start with all band flat cases. So basically, compact localized states occupy a single site by construction, how I construct it.
Okay, thanks.
Okay, Sergey?
Yeah, just to follow up on Bomjung on your very nice question. So why do you need the other flat band? That's excellent. Point is, I would maybe add to what Tilen said already is, if you forget about all the other bands from scratch and you are just left with one flat band, what you have a set of disconnected sites. Then whatever kind of disorder you throw onto that, nothing will happen except you will detune the energies, but nothing else will happen. They will be still disconnected sites. But if you have say two flat bands, then as we know, you can have well, Tilen showed how to get there, how to get to these so to say entangled or whatever through these unitaries, Kreuz ladders and the such. you get a more complicated lattice with non-zero hoppings, but it still has all bands flat. And it supports by that construction also compact localized states which are more extended. And now I guess when you start throwing in disorder, what happens is you start to hybridize these compact localized states. There will be non-zero matrix elements between them if you wish, and at very weak disorder, only the matrix elements matter between compact localized states originating from the same flat band. But you needed two flat bands or more in the first place. Otherwise, you would never get these hybridizations between these compact localized states. It's a very, very good question.
Okay. Any other question? Okay, if there's no further question, then I think it's time to move on. Okay, so let's thank the Tilen for this exciting talk. Yes, thank you very much. Okay, so let's thank all the speakers today, and it's time to close today's session. Okay, so thank you very much for your participation, and I hope to see all of you tomorrow. Okay, thank you very much.